Integrals of exponential and trigonometric functions. Integrals of exponential functions. From differentiation, we know that d e to the power of x dx is equal to e to the power of x, and d e to the power of ax dx is equal to a e to the power of ax, and d a to the power of x dx is equal to a to the power of x ln a, where ln stands for the natural log. From these, we can derive the following standard integrals for exponential functions. So the integral of e to the power of x dx equals e to the power of x plus c. The integral of e to the power of ax dx equals 1 over a e to the power of ax plus c. And the integral of a to the power of x dx equals a to the power of x over the natural log of a plus c. So ln stands for the natural log. So here we have page 26 of our formula book, and we can see these three integrals. Each of these standard integrals can be verified by differentiating the answer. Standard integral number 3 is obvious. And for number 4, d 1 over a e to the power of ax plus c dx is equal to 1 over a times a e to the power of ax, which gives us e to the power of ax. So to differentiate 1 over a e to the power of ax, we take the 1 over a outside, because technically that's the constant, and then we just differentiate e to the power of ax. So we bring the a down in front, and then we just have e to the power of ax. And to differentiate plus c, we just get 0. So then 1 over a multiplied by a is just 1, so you end up with e to the power of ax. And then d 1 over ln a to the power of x plus c dx gives us 1 over ln a, or the natural log of a, times a to the power of x ln a, which is equal to a to the power of x. So to differentiate this, we're going to bring the constant, which is technically the 1 over ln a, or the 1 over the natural log of a, outside the bracket. Then we're going to differentiate a to the power of x, and that's going to give us a to the power of x natural log a, or ln a. And to differentiate plus c, we just get 0. And then to multiply 1 over natural log a by natural log a, we just get 1. So we end up with a to the power of x. Evaluate each of the following integrals correct to 2 decimal places. Okay, so for the first one, we want to integrate e to the power of minus 0.1x dx between the limits 3 and 2. So we start off with the integration. So e to the power of minus 0.1x becomes 1 over minus 0.1 e to the power of minus 0.1x. So we got that from this integral over here, so from this statement. So since the power was minus 0.1, that becomes the a, so we get 1 over minus 0.1. Okay, so then that's between our limits 3 and 2. So we're going to substitute 3 in place of the x and minus our integral with 2 in place of the x. So we sub in the upper limit and then we sub in the lower limit. So this gives us minus 10 over e to the power minus 3, and down the minus, and this gives us minus 10 over e to the power positive 0.2. And then that simplifies to 0.78 correct to 2 decimal places. Next we want to integrate 2 times 3 to the power of x dx between the limits 4 and 1. So again we start with the integration. So to integrate 3 to the power of x, we're going to use this rule. So a to the power of x equals a to the power of x over natural log a. So instead of a to the power of x, we get 3 to the power of x over natural log 3. And we're going to bring the 2, which is a constant, outside the brackets. And then we're going to evaluate that between the limits 4 and 1. So the 2 is outside the bracket, and we have 3 to the power of 4 over natural log 3. We bring down the minus, and then we do the same with the lower limit. So we have 2 times 3 to the power 1 over natural log 3. and that ends up giving us 142.00 to 2 decimal places. Integrals of trigonometric functions. From differentiation, we know that d sine x dx equals cos x, and d cos x dx equals minus sine x. From these, we can derive the following standard integrals for trig functions. So, the integral of cos x dx equals sine x plus c, and the integral of sine x dx equals minus cos x plus c. So we can find these on page 26 of our formula book. Now the integral of cos ax dx equals 1 over a sine ax plus c, and the integral of sine ax dx equals minus 1 over a cos ax plus c. These are not in the formula book, you must learn them off. So this is page 26 of our formula book, and we can see those two integrals that we had a look at. So cos x becomes sine x becomes minus cos x. So to establish these standard integrals, we differentiate the answers. So d sine x plus c dx equals cos x, d minus cos x plus c dx equals minus sine x, which equals sine x. And d 1 over a sine ax plus c dx, we take the 1 over a outside the bracket, we differentiate the sine ax, which gives us a cos ax. The 1 over a multiplied by the a cancels, and we're left with cos ax. And d minus 1 over a cos ax plus c dx, we take the minus 1 over a outside the bracket, and then we integrate the cos ax plus c, and we get minus a sine ax, and the minus 1 over a multiplied by the minus a will cancel, and we're left with positive sine ax. Standard integrals 6 and 7 are on page 26 of the formulae and tables. Standard integrals 8 and 9 are not, and will have to be memorized. Find the integral of cos 7x dx. So we know from our formula book that the integral of cos x is sine x, but what we need to learn off is that the integral of cos ax dx is 1 over a sine ax plus c. So the cos will become sine, and the 7x will become 1 over 7 sine 7x plus c. So the integral of cos 7x dx is 1 over 7 sine 7x plus c. So we have to learn off this formula. Evaluate the integral of sine 3x dx between the upper limit pi over 4 and the lower limit 0. So we know that if we have sine x, then its integral is minus cos x. But we need to learn off that the integral of sine ax dx is minus 1 over a cos ax. Now usually we say plus c, but we don't include the plus c because we have limits. These are our limits. So the sine becomes cos, and the 3x becomes minus a third and 3x. So the integral of sine 3x dx is minus a third cos 3x. Now we want to evaluate this between these limits. But the first thing we'll do is take the minus a third, which is the constant, outside the bracket. So then we'll have cos 3 times pi over 4 minus cos 3 times 0. So upper limit, lower limit. So we still have the minus a third outside the bracket. Cos 3 pi over 4 is minus 1 over root 2, minus cos 3 times 0 is minus 1. And to simplify, we're left with 1 plus root 2 over 3 root 2. It may be necessary to use some of the trigonometric identities on pages 13 to 15 of the formulae and tables before being in a position to integrate certain trig functions. So evaluate the integral of cos x plus sine x squared dx between the limits pi over 4 and 0. After expanding, we will need to use the identities cos squared a plus sine squared a equals 1 and sine 2a equals 2 sine a cos a before integrating. So the integral of cos x plus sine x squared dx between the limits pi over 4 and 0. So multiplying out this, we get cos squared x plus sine squared x plus 2 sine x cos x. Now cos squared x plus sine squared x gives us 1, and 2 sine x cos x gives us sine 2x. So now we can integrate. So to integrate 1, we just get x. And to integrate sine 2x, we get minus a half cos 2x. And that comes from this formula here. So now we have integrated, we have to evaluate using our limits. So we take what's inside the bracket and we swap each x for pi over 4. So we get this. Then we have our minus. And then again we take what's inside the brackets and swap each x for 0. So we get this. And simplifying, we're left with pi over 4 plus a half. So this is page 13. That's the first trig identity that we used in that question. And this is page 14. That's the other trig identity we used. To integrate the product of two sines, two cosines, or a sine and a cosine, we can use the trig identities on page 15 of the formulae and tables to express the product as a sum or a difference. It is a good idea to write the product with the larger angle first. This avoids negative angles when the product is written as a sum or a difference. Okay, so let's evaluate the integral of sine 3x cos 5x dx between the limits pi over 8 and 0. So we're going to switch the sine 3x and the cos 5x. We're going to swap them around because the 5 is bigger than the 3. So we're going to have the integral of sine 3x cos 5x dx changes to the integral of cos 5x sine 3x dx. So we're swapping around so that the 5 comes first. We want the larger angle first. So cos 5x sine 3x. Hopefully you recognize this from one of your trig identities. And what it's very similar to is 2 cos A sine B. So instead of A we have 5x, instead of B we have 3x. But what's missing from what we have is the 2. So the 2 comes down here and becomes a half, and it goes outside the integral. And the reason for that is, if we have 2 cos A sine B, and we want cos A sine B without the 2, then technically what we have to do is divide by 2 to get rid of that 2. And if we divide by 2 on the left of the equal sign, we'd have to divide by 2 on the right of the equal sign. And dividing by 2 is the same thing as multiplying by a half. So you'd really be multiplying all of this by a half. So that's why the half gets stuck outside the integral, because it's a constant. So then we use our formulas. So sine A plus B becomes sine 5 plus 3, which is sine 8x. And then we have the minus. And sine A minus B becomes sine 5 minus 3, which becomes sine 2x. So we have a half, and then we have the integral of sine 8x minus sine 2x dx between the limits pi over 8 and 0. Okay, so next we integrate. So sine 8x, so we're going to use this formula up here. So since we have an 8 in place of the a, we're going to have minus 1 over 8 cos ax. So minus 1 over 8 cos 8x. And then we have the minus. And then sine 2x. So instead of a 2 here, instead of an a, we have a 2. So we're going to have minus 1 over 2 cos 2x. So minus minus gives us a plus. And remember, you've still got the half in front. Okay, so now we're going to sub in our limits. So we take what's inside the bracket. We sub in pi over 8 in place of all the x's. And then we have a minus. And then again we take what's inside the bracket and sub in a 0 in place of all the x's. And the half again is still in front. Okay, and then we can see we've multiplied out our brackets and simplified, and we end up with 2 minus root 2 over 8 root 2. So this is page 15, and this is the identity that we used in the example. To integrate a cosine squared or sine squared, we can use the identities. Cos squared a equals a half times 1 plus cos 2a, and sine squared a equals a half times 1 minus cos 2a. These are on page 14 of the formulae and tables. So let's evaluate the integral of cos squared 4x dx between the limits pi over 8 and 0. So from our identity, cos squared a equals a half times 1 plus cos 2a, we get cos squared 4x equals a half times 1 plus cos 8x. So since this is a 4, and this says 2a, so if a is 4, and here we have 2a, 2 times 4 is 8, so that's where the 8x comes from. So the integral of cos squared 4x dx is equal to a half, so we're bringing the half outside the integral, times the integral 1 plus cos 8x. So again, we got the 8x because 2 times 4 is 8 dx. So the half is still outside the bracket, and now we're going to integrate 1 plus cos 8x. So the integral of 1 is x, and the integral of cos 8x is going to be 1 over 8 sine 8x. So we got that from up here. So swapping this a for 8. So now we can evaluate using our limits. So we sub in pi over 8 for each of our x's with brackets. Then we have a minus, and then we sub in 0 for each of our x's with brackets around it again. And again, remember we have the half in front. And this simplifies to be pi over 16. So this is page 14 of our formula book, and here are the two formulas that we were looking at in the last example. So we used cos squared a in the last example, but if there was a question involving sine squared a, we could use this one.